Okay, in this video, so by the end of this video, you should be able to, which I forgot to write here, describe the electrophilic substitution of arenes with concentrated nitric acid, and that should be concentrated sulfuric acid. I've put it in brackets because it actually acts as a catalyst and is not really a reagent. We want to describe the electrophilic substitution of arenes with halogens in the presence of a suitable halogen carrier. Okay, so halogen carriers we've not met before, but they're pretty simple. I'll explain those when we get to them. Okay, so benzene undergoes electrophilic substitution. I'm just going to shorten substitution to that. With electrophiles that are attracted to the electron-rich benzene ring. So lots and lots of electrons in benzene rings, 6 electrons. Electrophiles, things that love electrons, are attracted to them. Okay, so first one we're going to look at is nitration. So in nitration, if we have our molecule benzene and we have HNO3 and we do this in the presence of H2SO4 and we warm it gently, we will make nitrobenzene. Add a bit of water. Okay, so here we have nitrobenzene. Okay, so nitration, adding NO2 nitrate. Okay, so HNO3s are reactive species, and we've got H2SO4 as a catalyst there. Okay, and then we have halogenation. So we take benzene, and if we add Br2, and we're going to use, let's say, iron tribromide as our kind of catalytic species, and we will make this compound here, and a bit of HBr, and this FeBr3 is our halogen carrier. Okay, and I'll show you what that does in a bit. And this is bromobenzene, so we've done a bit of naming these types of compounds a long time ago. But that is bromobenzene. Okay, now we need to know the mechanisms for both of these reactions. So mechanisms are very, very similar. Okay, so in your notes, you may want to put nitration and the mechanism for nitration together, or halogenation and the mechanism for halogenation together. But I put the reactions and the mechanisms separate, because what you see, if you have both mechanisms next to each other, you'll realise they are very, very similar. Okay, so nitration, we're going to do in green. Okay, so HNO3 plus H2SO4 generates NO2 plus HSO4 minus plus water. And this NO2 plus is a really, really good electrophile, or what we might call a powerful electrophile. So powerful, in fact, that the electrons from the benzene ring, a pair of electrons from the benzene ring, will attack that electrophile, and they will form a bond between this carbon, or any carbon I suppose, and the nitrogen. So we are left with this carbon with a bond to hydrogen and nitrogen, and the electrons in the ring are now not complete. So there were 6, there's now 4. So actually, there is a plus charge, kind of over all the carbons, but probably slightly located more on this one here, okay? But it's generally spread out. And what happens is this hydrogen will drop off, and drop off as an H+. In order to do that, both the electrons from this bond are donated into the ring. So this bond breaks, and its electrons go into the ring. So we restore our 6 electrons. And we're left with NO2 and H+. This H+ reacts with the HSO4- down here. To regenerate H2SO4. So that's why I said that sulfuric acid acts as a catalyst here, because we're regenerating that starting material. Okay? And obviously the water, which is made here, is what we talked about here. Okay? Right, second mechanism, halogenation. We have our bromine and our iron tribromide. This iron tribromide is a halogen carrier because it reacts to make Br plus and FeBr4-. And this Br plus is a really, really good electrophile. A polarized bromine molecule, delta plus and delta minus, is not a good enough electrophile for the benzene ring to attack it. It needs to be a wholly positive bromine ion. Okay, so you're starting to see some parallels between these mechanisms. So the electrons from the ring attack the bromine. They form a bond between this carbon and that bromine. Okay, so that's why I draw the arrow going past that carbon, because it helps to indicate that. We get a positive charge on the ring, HBr, so again we're seeing some parallels. So the ring is broken up, we haven't got all its electrons. H bond breaks, and the electrons go into the ring. Forming bromobenzene. And H+. The H+ and the FeBr4- react to make HBr and FeBr3. Okay, so again, when we look back at our original equation, this is on top, it's a halogen carrier. We could say it's a catalyst, but to be more specific, we want to say halogen carrier, and we're getting HBr as well. Okay, so two mechanisms, very similar. So really similar, guys. You can see both steps mirroring each other, but you also do need to know how you're generating your electrophiles. Okay. All right. So those are the two reactions we need to know about: electrophilic substitution to do nitration and to do halogenation. Exactly the same for chlorine, except you will use a slightly different halogen carrier, which I'll tell you about in the lesson. Okay.